subgroups, the axioms. We'll let G under composition be a group with the identity element E, and let H be a subset of G. Then H under composition is a subgroup of G under composition if and only if the properties below hold. So as usual, closure, identity and inverses. For all x and y in H, the composite x composite y is in H. And our identity element is E. So of G is contained in H. Inverses for each x contained in H, its inverse of x in G is also in H. So here's an example. We'll show ERST under composition is not a subgroup of S square under composition. Now answer, we have this we assume is a subset of S square, and the binary operation under composition is the same on each set. However, RT is contained in ERST, but R composite T equals B, which is not contained in ERST. So axiom 1, closure, fails. Hence, this is not a subgroup of S squared under composition. Now, if you remember before, these are all our symmetries of the square, and these are the reflections, and we have rotations A, B, C, and so on. Now, example, show EABC under composition is a subgroup of S square under composition. Now, the answer, we have EABC is contained in S squared, and the binary operation composition is the same in each set. We construct a Cayley table. This is a Cayley table, by the way, where we're just writing out values. A under the E identity is just A, and so on. E under A, and then all the others. So our Cayley table for EABC under composition, by reflecting unwanted rows and columns of the group table S squared under composition, the Cayley table for EABC under composition is given here. We check the three subgroup properties. We use the table to check axiom 1 and 3 to check the inverses. Look for occurrences of the identity element in the table. So axiom 1, closure. Every element in the body of the table is in EABC, so EABC is closed under composition. Axiom 2, identity. The identity in S squared is E, and E is contained in EABC. So axiom 2 is satisfied. Axiom 3, inverses. The element E and B are self-inverse, and A and C are inverses of each other. So EABC contains the inverse of the elements. Hence, the set EABC under composition satisfy the axioms, so is a subgroup of S squared under composition. Now here's another example. We'll show the positive integers under multiplication is a subgroup of the integers which the non-zero integers under multiplication of real numbers. Our positive real integers is a subset of our real integers without 0, and the binary operation x is the same on each set. Now axiom 1, closure. We check x and y is contained in the positive integers, then xy is contained in R. X is greater than 0, y is greater than 0. It follows that x multiplied by y is contained in R, and x multiplied by y is greater than 0, so x multiplied by y is contained in R plus. Thus R plus is closed under multiplication. Axiom 2, identity. The identity element in R star under multiplication is 1, and since 1 is greater than 0, 1 is contained in the positive integers. And axiom 3, inverses. Let x be contained in our positive integers. The inverse of x in our non-zero integers under multiplication is 1 over x. Since x is contained in our positive integers, we have x is contained in our integers, and x is greater than 0. It follows 1 over x is contained in our integers, and 1 over x is greater than 0. So 1 over x is contained in our positive integers. Thus, our positive integers contains the inverse of each of its elements. Hence, r plus under multiplication satisfy the axioms. So is a subgroup of r star under multiplication. And that's the end of this lecture. Please do like and subscribe.